That's why
Yeah, so I'm going to use this for a few minutes and then I'll switch to the other.
That one's there. So
Yeah,
you just need to
right, and then I'm going to switch to this one. Oh, I see. So how do I switch?
You just click on that one.
Where is the second one?
There.
Yeah, but where do I click on?
Oh, you just click on the top line.
Oh, I couldn't see it. Yeah, okay. That's good.
So it's very easy to switch. All we need to do is to turn on recording. So this is the one you're going to start with, is it?
Right, I'm just going to review what I did yesterday.
So we're ready to start, except I know it's up to you how long the break is, but
I want to call them. Look, is the title of your talk still about
Yeah, it is. Or you could just say algebra.
All right.
The title of my talk is algebra.
Can I say, Lou is going to talk about everything she thinks at the moment?
No, you can say Lou's going to talk about algebra. It's about algebra.
I was pulling you already.
Yeah.
No, that's starting.
okay, start.
Okay, wake up.
Recording in progress.
Yeah.
It's all out of the way.
Okay.
Mike's all yours.
Okay.
All right. So, we have the last talk of this morning, and there is no need to introduce Lou. Everybody knows you, Lou. And Lou is going to talk about algebras.
That's right. And I'm going to begin by just very quickly reviewing what I did yesterday, drawing on a pad. So I made a very short show. And we were talking yesterday about knots and links. And I pointed out that there are these three moves, which I have drawn here. A little twist, a bit of rope that goes behind another bit of rope and comes apart, and another one where a piece of rope is underneath another piece of rope and goes down underneath the crossing, like that. And it turns out that the topology of rope in space, three-dimensional problem of it, are two entangled messes of rope, are they equivalent to one another, is whether or not you can get from one to another in the diagrams by going by these moves. That was proved by Reidemeister and Alexander and Briggs back in the 1920s. So that's a very beautiful fact that the topology of this very complicated entanglement in space can be reduced to three simple graphical moves. That's what I was saying yesterday. And then I was also talking about this logic of elementary discrimination that's very simple and involves a triplicity. And this triplicity takes you to three-dimensional space in a kind of a deep way. So if you look at it, what I'm saying is that I have three entities, and if I combine any two of them, I get the third. And this reminds you of other things, of course. It reminds you of I, J, and K, where I times J is K. It reminds you of that, but it's not quite the same. This one's commutative. There's no signs, but it is a little like the vector cross product or the quaternions, except that we've made a certain choice about what happens to the self-interaction. The self-interactions are that they interact with themselves to produce themselves. They interact with another to produce a third. And in that algebra, you find that there is intrinsically in it relations to the topology of three-dimensional space. In the other algebras that you already know, the quaternions, for example, where you have A, B, and C, again, only you're calling them I, J, and K, and you have I squared and J squared and K squared are minus 1. It's another story, but it's related to the rotations of three-dimensional space. So in both cases, these kind of algebras are related to some deep thing about three-dimensional space. In this case, what I was remarking last time was that you can relate it to topology in three-dimensional space by coloring the edges of a diagram of a knot or a link or a braid with the A, B, and C. And when two of them are colored, then you color the remaining one with the product. And I take the product in the order A times B. although in this case it didn't matter, but in other cases it will matter whether I did A times B or B times A. In this case, it doesn't matter. I just take the product. And you will note that this algebra that we talked about before is non-associative. But vector cross product algebra is non-associative. If you take A times B, you get C. If you take A times AB, you get B. Not associative. And then you can see that everything works well with regard to those moves. This is supposed to be A, B, and C that you're looking at. So A interacts with A to produce A. So it's the same whether you had the twist or you didn't. A interacts with B to produce AB, and then it meets B again. And A times B is C, and C times B is A. So you came back to A. And so it didn't matter whether you pushed it in or not. And the other one works out just as well. If you take the triangle, then you find, as we found before, that what needs to happen is that it should distribute over itself. And that, in fact, is true. If you're using A, B, and C according to our rules, A, B is C, and C times C is C. A times C is B, B times C is A, and A times B is C. So you got it in both cases. And it works. And that means that you can see colorfully that some things are knotted. For example, here's a trefoil knot, and I can label the arcs in the trefoil knot by the 3 colors. So we could do it with colors. And then you see I have these 3 colors, which I've denoted by blue and red and green, apparently. And I start pushing the knot around. And when I push the knot around, then those very bits of algebra that you saw before are telling me that the coloring will work out all right. I pushed red up against blue and then underneath it, and it turned into green. That's right. And then I pushed it again under red, and it turned into blue. And then I pushed it under green, and it turned into red. And then I pushed it under red, and it turned into red. So that whole line of pushing, and it's still colored. And then I moved it across the triangle, and it remained colored as we saw that it would. And if you think about that a little bit, you realize that if you started with a colored trefoil knot, and then you start pushing it around topologically, making some other knots out of it, some other knot diagrams out of it, they're all going to be colored with 3 colors, no matter what happens. And so there's no way to get to the unknot, which is only colored with 1 color. And therefore, we prove that the trefoil knot is knotted by seeing how it can hold these colors in that way. So this discrimination system is actually discriminating the topology of the trefoil knot. And so that's an example of doing something that is not so easy to do with a Boolean look at things. And of course, we also did this. We were remarking that we could see that a weave would be different by watching what happens as you go down through the weave. So I just thought I would start with that because I had drawn it on a piece of paper, and many people over there on the other side of the Zoom didn't see the paper anyway. So this is just to be complete about that. And now let me see here. The other file needs to be selected. Let me just select. There we go. Okay. So this is the algebra talk. And I'm talking about Clifford algebras. I will get to Clifford algebras, but what I wanted to do, I would like to get to more physics, but this is mostly a math talk. And so you can relax and not worry about the nature of physics for this talk. And what I am concerned with here is the nature of algebra. Algebra is a kind of mysterious subject, right? You decide that you're going to have some rules for combining various letters, and they form interesting structures like the ABC algebra we just looked at. And why does that end up working, and what's involved? Well, it's certainly a simple idea, and it goes way back in history, that we can write down letters for numbers or some generalized numbers, and we can write down how they combine, and then we can start studying how they combine, And we get a lot of mathematics out of that, and we get a lot of insight about all sorts of things, geometry, physics, algebra itself. It's kind of mysterious that you can do that much with just the way things combine along a line with letters. It isn't obvious that this would do as much as it does. So I'm going to look at things historically. So what did I write on this slide? I said there are 2 points of view. There's the mathematical point of view, so operations on pairs of things, symbols maybe, and then there's the physical and geometrical. You often can interpret these algebras, or they come from something physical or geometrical. Like in the case of the algebra that we just mentioned, we can make that immediate jump. In this case, it's rather nice. You can make this immediate jump between the algebra, its abstract discrimination property, and labeling something geometrical, the knot diagrams, and then seeing how it interacts with them. In topology, we like that if we can do it, if we can get algebra to interact with topological structure in some way. And that example was really sort of the best kind of example of algebra and topology working together. But if you think about ordinary arithmetic, you also have diagrams for it, but maybe you forgot because of the way you were taught arithmetic, that you can think of the numbers as rows of dots or collections of dots. So I can represent the number 2 by 2 vertical lines, and the number 4 by 4 vertical lines, and the number 10,000 by 10,000 vertical lines. Well, it gets out of hand, doesn't it? But for small numbers, you can understand how numbers interact by saying, okay, 2 plus 2 means that I put them together and I get 4. So there's the proof that 2 plus 2 is equal to 4, right? And what about multiplication? So I'm going to talk about things for a while, just elementary things, and we'll walk up through the history of things and see where some algebras came about and how people interpreted them, and then try to look at some different interpretations. So how do you multiply? If you're thinking diagrammatically, you think, well, I'll use one of the numbers as a template for making that many copies of the other number, right? And now I have a physical way to multiply. 2 times 3 means that I look at the 3 on the right, and I put one copy of 2 for each bar in the 3, and now I've multiplied 2 times 3. Now you need to prove that 2 times 3 is equal to 3 times 2. Maybe you want to think about that. I don't think I drew a picture of it, but there's a picture of it. And so we know how to multiply and we know how to add. So this is all arithmetic from that point of view. There are some questions, though. One question is, well, what do I do with these things if there's no room to write them anymore, right? And of course, as you know, people developed abbreviations for numbers, which let you write much larger numbers, but you still always run into that problem of being unable beyond a certain point to actually represent a number. If I take a number like 10 to the 137 and I ask you to write it out in terms of dots or marks, you can't do it. You can't do it. So it becomes an idealization. The numbers become idealizations of numbers after a point. But there are properties, and we can see properties of numbers in general. So, for example, 1 plus x is x plus 1. Or more generally, x plus y is y plus x. And why is that? Well, you have a row of marks for x and a row of marks for y, and you want to see that it's not going to change. You can move one of them up around the other one and put it on the other side. And the total number of marks didn't change. But there's a concept there. So at some point, people began to understand the concept that 2 collections of dots would represent the same number if you could put them into one-to-one correspondence. So the 4 dots over here that are in a square form can be put into one-to-one correspondence with the horizontal 4 dots, can be put into one-to-one correspondence with the vertical 4 dots. And certainly if I move dots around, I'm not changing the one-to-one correspondences that I might have made. And so I can see that x plus y is equal to y plus x. And it's clear that that works for any numbers of any size. These are proofs at some level. Oh, I do have two. I proved here that 2 times 3 is 3 times 2. I meant to prove it. I didn't remember whether I got it. Can you read my proof there at the bottom of the slide? I did 2 times 3, and that meant 3 groups of 2. And I wrote 3 groups of 2 in vertical dot form. So I have 2 dots, 2 dots, 2 dots. It's 2 by 3. But 2 by 3 can be rotated until it's 3 by 2. And then it's 2 groups of 3. So multiplication is commutative. So you can think of arithmetic that way and never think about it any other way for a long time, but certain other things come in. I'm sorry, that slide is a little hard to read, but I wanted to mention that looking at algebras as coming from interactions of things is natural in lots of ways. For example, Dennis was talking yesterday about how he thinks of the fundamental kind of algebraic or numerical or mathematical interaction as composition of permutations. And composition of permutations is certainly really down there in the bottom, and you can draw pictures of those in the same way as you can draw pictures of interactions of numbers. I take a collection of lines that cross one another and think of it as a permutation. Like what I drew here was the first one goes to the third one, the second to the first, and the third to the second. That's a permutation. And in the usual terms, I wrote the usual terms. But the point is that if you have a permutation drawn that way, and you have another one drawn that way, then you plug them into one another and then see where things go. So you plug 2 permutations into one another somewhere here, like this one over here, sigma tau. The first one ends up at the third. The second one ends up at the second, and the third one ends up at the first by plugging in and following the line down. So that's the combinatorial rule for combining the permutations, which you can make algebraic. And so the theory of permutations also, just like the theory of arithmetic, can be interfaced with what happens with these kinds of combinatorics. And the same is true of braiding, as we were mentioning yesterday, where, as you see, braiding is some kind of generalized permuting, where not only are you permuting, but you're keeping track of which way you turned around when you did when you permuted 1 with 2. You turned around this side, or you turned around the other side. And if you did it twice, you don't come back to where you started because of the fact that you're circling around. So braiding is generalized permutation, and really does need to see how one interacts with the topology of the diagrams. And then there are other things like, what did I draw here? What's called temporally leave or connection algebra, where I'm allowing that things will turn around. So I may go from a point back to a point on the top, as well as going from a point to the bottom. And you can still plug things in that way. And then you get all kinds of structures that turn out to be useful in various places, like in statistical mechanics and in topology. So there are lots and lots of ways to make algebras out of geometrical situations by watching how things combine. And I just wanted to add that into the story. But now we're going back to arithmetic and thinking about it a little further. Whoops, why did that do what it did? Okay, so if I'm thinking about arithmetic in this combinatorial way, then I can perceive truths of arithmetic up to a point at least by just watching what happens to the pictures. So for example, you may know this one. I have a square here, 3 squared, right? And I look at 3 squared and divide it up into 1 by 1, and then there's that next little L, which is 3, and the next L shape is 5. And so I see that 3 squared is 1 plus 3 plus 5. And I see quite clearly, looking at that if I had gone to 4 squared, then I would have 7 on the next L. and I would have 1 plus 3 plus 5 plus 7 would be 4 squared, and 1 plus 3 plus 5 plus 7 plus 9 will be 5 squared. And I see that it's true that if I take the sum of the first n odd numbers, I will get n squared. I see that. I can just see it directly. So that's an infinite number of specific truths of arithmetic that you can just see directly by looking into it that way. And there are lots of things like that that you would like to see this way. For example, the square root of 2 is irrational. What does that say? It says that if the square root of 2 is equal to p over q, then 2 would be equal to p squared over q squared. And that says that 2q squared would be equal to p squared. It says that if it were rational, it says that there would be 2 squares that could be rearranged into 1 square. 2 squares of the same size, like 3 squared plus 3 squared, should be equal to some square. But 3 squared plus 3 squared is 18. It's not a square. And that the square root of 2 is irrational is saying that you're never going to find a square number which, when you add it to itself, will be a square. Right? That's what the discrete version of that is. And then you can try, and I didn't put it in the slideshow, to make a picture proof of that. It's possible. It's possible to think about how squares of dots could possibly be rearranged and see that you can't rearrange 2 copies of a square of dots and make a square out of it. I'm not saying you see that immediately, but there's a picture proof of that. But then you can go up into other questions about the truths involving numbers, and they get harder. The Fermat theorem, for example, says that a cube is never equal to the sum of 2 cubes. That's what it says, right? X cubed plus y cubed equals z cubed has no solutions. It isn't, those 2 cubes don't have to be the same anymore. It's like the irrationality statement. There's no way to take 2 cubes and turn them into a cube. Well, I would like to see a proof of that by thinking of a cube. A cube is a cube of dots, right? There it is in front of you, a nice cube of dots, like my picture on the page, but 3-dimensional. And you want to see that you can't take a cube of dots and another cube of dots and somehow rearrange them and make a cube. But I don't know a pictorial proof of that. If I look in a book on number theory, I see a rather complicated analysis for the Fermat theorem, even in the case of n equals 3. So these things get away from you. We don't have the ability to see in to everything immediately. It would be nice, but that's always there. There's that tension there in every piece of mathematics that I know. That it always begins with something that is almost manipulable by hand. And you can make a lot of reasoning on that basis, and then it begins to get away from you, and you need to try to do it in a more abstract way or to find a concept that you're missing, and it's always that way. It's very interesting.
I mean, I was just kind of guessing. I was just guessing about your. Or shall I wait to the end? I mean, I was just guessing about the 2 squares, and just thinking, well, you could do it pictorially. The way I thought of doing it pictorially would be to start with.
Yeah, go ahead and guess, but I think we should talk about it afterwards because all our guesses don't quite work, and then eventually they work in it, and you say aha, but it could take a while.
Yeah, but then let's talk about it later.
Right, but that one's doable. It's doable to prove that the square root of 2 is irrational by seeing that you can't combine 2 squares to make a square.
Yeah.
The next one up, I don't know. That Fermat one. Yeah. Or for that matter, I mean, Fermat's general theorem says that if you take an n-dimensional collection of dots in the form of a of an n cube, the analog of an n cube, an n hypercube. You can't combine two n hypercubes to get another n hypercube, right?
That means it's like
Why?
like
Mr. Wiles tells us why, but he uses a lot of things to do so. Yeah.
Does that mean that it's like not close? Like, so you can't take 10 n cube numbers and then combine them together to get another n cube number. That means that addition wise, those two n cube numbers wouldn't be closed under addition.
Well, we have closure, of course, right? I mean, two numbers add to two numbers.
I mean, like,
But Fermat asserts that two cubes do not add up to a cube.
So there's
So you don't have closure.
Yeah.
Right. But it's not so easy to see that you don't have closure. Right? I mean, it works for squares, right? I can take 3 squared and add to it 4 squared. I get 5 squared. So, but that's the last time that kind of thing works. As soon as you go up to cubes or higher powers, it doesn't work anymore.
Is there any physical significance that squares as privilege?
Yeah.
I would have thought.
Right. So you would think that you can also ask, what is the physical significance of that, right? Is there some physical significance to the fact that we have Pythagorean triples, but we don't have any higher?
We have squares everywhere in our physics.
Yeah.
We don't have cubes very much.
Right. Well, as I started to say on this slide, now Frege and Peano in the 1800s, they axiomatized the natural numbers. They weren't axiomatized before. The way I've been talking about arithmetic up to this point is more or less the way people did arithmetic. They could write it down algebraically. They also thought about it geometrically, all the way back to the Greeks and beyond, and forward up until modern time. But then these people started to think, well, I wanted to axiomatize it in such a way that I don't have to think of the number as physical at all. I don't have to worry about how many marks I had to make in order to get to the number. And what does the axiomatization look like? It looks like this. Do you remember this? Have you ever studied this? It's very interesting, but if you try to work from the axioms, you have a lot of hard work to build up to things that we were naturally just doing a few minutes ago. You say there is a number 1, and given a number 1, there is a number 2 and a 3 and a 4, because you can always get a successor. So you give a rule that says if I have a row of marks, I can make another row of marks by putting one more bar on it. Okay, fine. And then 2 extra rules. If the successors are equal, then the predecessors are equal, and you never get back to 1. And that's enough. That makes sure that you can make rows of bars that will always be different, and going on and on and on. And then the principle of induction, that if something is true for 1, and if you know that when it's true for x, it's also true for x plus 1, then it will be true for all numbers. And we're all familiar with that principle. But that is modern times. And now you can prove things using that for all numbers by appealing to the induction principle, right? You don't have to just appeal to the fact that you see the pattern. Well, that then suffuses everything with that axiomatic intent, and I wanted to mention. Now, another thing that happened, of course, was that once people had algebra, they could solve equations, and people learned long ago to solve quadratic equations, just like you did long ago. And when people learned to solve quadratic equations, they were puzzled by the fact that the discriminant, the part underneath the square root, could be negative. It's perfectly possible for it to be negative. And if it's negative, then you might get something like this: x squared plus x plus 1 equals 0. And I read off the solution, and it has the square root of -3 in it. And what's that supposed to be? Now, you already know the answers that have been around since the 1800s, right? That you can interpret the square root of a negative number in terms of the geometry of the plane. But back then, it wasn't there. It wasn't there. It wasn't there in the 1500s when Cardano and Tartaglia started figuring out how to solve cubics. It wasn't there. It was almost there near the end of the 1600s, as I'll show you in a moment. But it didn't really come into focus until around 1800. So there was this long period of time where these square roots of negative numbers were being used by people, but they didn't know what they meant, and they wondered what they meant, but they were curiously just going ahead and using it as a formalism to see what they would get, and they got very interesting things. So, for example, Cardano and Tartaglia figured out how to solve the general cubic equation. Now, if you draw the graph of a cubic, it looks like that, you know. It's got a maximum and a minimum, and it always goes through the real line, so it always has a real root. So they, among other things, figured out how to write down a formula for the real root. But their formula involved imaginary numbers. I'll show you a formula in a moment. I'm not going to go into the details of this slide other than that, so let's just go to the next slide. They could, if Cardano and Tartaglia were handed that cubic there, which I have plotted just to show you that, it seems to have 3 roots, 2 of them are negative, and one of them is 4. And you can see it's true. 4 cubed minus 60 minus 4 is equal to 0, right? So it's got a root 4. But if Tartaglia was given that and he didn't notice that it had the root 4, he would have written down, yes, it's the cube root of 2 plus 11i plus the cube root of 2 minus 11i by his method. So they were puzzled by this. I mean, they could write down real roots of cubic equations by these mysterious expressions involving I, and they had no idea really quite exactly why that's working. You know why it's working. You'll notice you do know why that's working, right? Because you interpret 2 plus 11i as a certain vector in the plane up here, and the cube root is the principal cube root, so you just take 1/3 the angle and take the square root of its distance, and it's another vector above the axis. The other conjugate is below the axis, and you added those 2 vectors together and you got some positive number. So it's got to be the positive root, and therefore it must be equal to 4, because that's the positive root. So by knowing the Gauss-Argand interpretation, which came around 1800, you understand completely why it ended up being 4 and not one of the other roots, for example. You understand everything because of that interpretation. But they didn't understand it was a mysterious symbolic method. Well, I wanted to talk about getting there, and Wallace, John Wallace, who was an Oxford mathematician, around 1670, he said this. He didn't say it quite as blatantly as I'm saying it here. If he had, it might have promulgated. He said, look, it's a theorem of geometry that if I have a right triangle and I drop a perpendicular from the 90-degree angle down to the hypotenuse and divide the hypotenuse into A and B, then A is to H as H is to B, because of similar triangles. And therefore, H squared is equal to AB. And therefore, H is the square root of AB. That height of the drop from the 90-degree angle to the hypotenuse is equal to the product of the lengths on either side of the drop, the square root of it. But then he was also one of the first people to promulgate and write in an algebra text about negative numbers. And so he said, well, what if we put the triangle so that the height drops to 0 and we have -1 on one side and +1 on the other side? Then the geometry formula says that H should be equal to the square root of -1 times +1. Square root of -1. So that the height of a line, the line perpendicular to the real line going above the origin like that should be the square root of -1. So he said exactly what became the interpretation 130 years later in his algebra book. But of course he said it more obscurely than that, and also people had not absorbed the idea of the Cartesian plane, of the pairs of numbers that would correspond to points in the plane and all of that. So by the time 1800 came along, Gauss and Argonne used exactly that same idea, and they didn't have to base it on a weird geometric observation, and so it became standard litany, that you could think of complex numbers this way, as I minus 1 and 1, and A plus BI out there like that, and the way we think about it. And then when that came through, to understand that they were rotational, that I rotated by 90 degrees, and that with Euler, e to the I theta rotates by theta, and all of that, But even then, it was until around 1840 or maybe a little earlier that Hamilton comes along and says, well, you can be very simple-minded about this and just think that I is an operator which takes a pair AB and turns it into the pair minus B comma A, which of course is what happens when you multiply I times A plus IB. So that made everything really concrete. You could eliminate all these funny symbols and just say that I multiply couples. That's the way Hamilton liked to think about it. You have a couple AB and another couple CD, and you have a product formula for them. AC minus BD, BC plus AD, of course. And once that was in, along with the geometric interpretation and everything, people became completely satisfied with this, that it's just a form of pairs of numbers, ordinary mathematics with pairs of numbers. They stopped worrying about the mysticism of it. But the mysticism was there for a long time, and maybe rightly so, in the light of other remarks we've made about it, right? That you should think about it philosophically. For example, Leibniz said that the square root of -1 is an amphibian between being and non-being, right? So we shouldn't forget. But now I wanted to go through my history, and I may be running out of time, so let's move a little. Come on.
5 minutes left.
There, okay. How are we doing? Well, we're all right. So around 1843, Hamilton invented the quaternions after 15 years of searching for some way to generalize the complex numbers into 3 dimensions. And what was obstructing him was that he really needed to go to 4 dimensions to get the symmetry of the situation right. And he went to 4 dimensions in 1843, and as you know, he inscribed this equation on the Brougham Bridge in Dublin. And to this day, you can find the plaque on that bridge with this information, not the original straw. And so the interpretation here is that I, J, and K span a 3 space, and the extra scalar, which I've drawn as a green arrow, is the 4th dimension. And that's written as just multiples of some number. So a quaternion could be something like 1 plus 3i plus 4j plus 5k, right? And this is non-commutative, right? ij is not equal to ji. That's the first instance of someone writing down a non-commutative algebra, as far as I know. And the quaternions are associative, and they have inverses for non-zero elements. And those are all the things that Hamilton wanted. I guess he must have known in trying to do it that it would be non-commutative, but he couldn't get it to quite work until he got to 4. But in the same year after Hamilton communicated this to him, Graves invented the octonions, which is one more generator, pumping it up to 8 dimensions, square root -1, and non-associative, but very clever algebra. And then this was but Graves didn't publish it. And in 1846, Cayley rediscovered it. So that gives now you have these algebras, non-commutative algebras. You have the real numbers and the complex numbers, and then you have the non-commutative quaternions that are associative, and then you have this analog octonions or Cayley numbers that are non-associative. And getting back to quaternions for a moment, if you have an arbitrary quaternion, I've written an arbitrary quaternion, Q plus AI plus BJ plus CK. That's Q plus a vector. Q is a scalar. It's in the fourth direction, right? And I want to know how to multiply quaternions. Well, the scalars just multiply as they usually do. So the real question is, how do I multiply two of the vectors together? And the answer in terms of modern notation, which wasn't probably a notation available to Hamilton, is that V times W is minus the dot product of V and W plus the cross product. And if you think about what you know about those, you see that's right. If you take I times J, for example, then I dot J is 0 because they're perpendicular, and you get the cross product of I and J, and that's K. Okay, I times J is K. If you take I times I, then you get minus I dot I, which is minus 1, because I is a unit vector, and its dot product with itself is 1, and I cross I is 0. Cross product of a vector with itself is 0. So this is the general formula. But the general formula shows you some things that you might find a little surprising if you haven't thought about it before. Suppose you take a unit vector and multiply it by itself. Well, the unit vector times itself is 0, and the unit vector dotted with itself is equal to 1. So any unit vector in three-dimensional space is the square root of minus 1. So in the quaternions, the entire sphere surrounding the origin has square minus 1. Every point on it has square minus 1. You have infinitely many square roots of minus 1 instead of only 2, as you did in the complex numbers. And of course, the vector cross product is non-associative, so somehow this dot product vector cross product combination ends up producing an associative algebra, and that's a very interesting exercise to see why that's true, to think about why that's true. And this formula should be taught in every course in advanced calculus, but it isn't, because there was a quaternion wars in the 1800s, where people were fighting to get rid of the quaternions from the language and put in place for that cross products and dot products and all the other vector operations that we're familiar with, because they felt it was easier for people to deal with, particularly for working with electromagnetism and things like that. So when Gibbs wrote his famous book on advanced calculus, the quaternions were not mentioned. But as you see, the quaternion product is just given in terms of dot products and cross products and would make a good small chapter in any book on advanced calculus. Well, actually this happens now because quaternions can be used for rotations in computers, computer graphics, and so there are lots of books about how to use quaternions, but it's still the case that most advanced calculus books don't mention them. I don't know why.
Physics courses. Physics courses don't do them.
And of course, physics books often mention quaternions. That's right. The mathematicians sort of lag behind here. Now here's a famous formula about the Cayley numbers. This is called the Cayley-Dickson formula. It was formulated by Dickson sometime later. Did I make a mistake in this slide? No, it's just hard to read. That's A plus JB times C plus JD, okay? And J is my brand new square minus 1 element, okay? This is generating new algebras out of old algebras. I have an algebra involving the small letters A, B, C, and D, right? And it could be the quaternions, or it could be the real numbers, or it could be the complex numbers. It could be some algebra, and it has to have a conjugation. For example, quaternions have conjugation. The conjugate of x plus iy, j, z, k, w is put minus signs on the I, j's, and k's, okay? And if you multiply a number by its conjugate in the quaternions, you get the sum of the squares. That lets the quaternions, if you handle them with an extra square root of minus 1, give you the Minkowski norm and all that. But anyway, the product of two things, conjugate, is the reverse product of their conjugates, because the quaternions are not associative. So I'll assume that I'm not commutative. So I'm going to just assume that. I have an algebra and I have a conjugation, and if it's non-commutative, then the conjugate of the product is the reverse product of the conjugates. That's given, okay? And now we're going to form a new algebra consisting of things of the form a plus jb, and j squared is minus 1. And this formula, like the formula for multiplying complex numbers, tells you how to multiply them. And it's a little finicky. You see, you multiply a times c, okay. But you have minus db bar. So that had to do with j squared being minus 1, but then the b and the d reversed their locations, and one of them got conjugated. And similarly for the other part. This isn't, I never memorized this formula, but this formula works. So, I'll finish my sentence. So, for example, if you start with quaternions and define a new 8-dimensional algebra using Cayley-Dixon, you get the Cayley numbers, okay? And if you start with the Cayley, and it's not associative, but all the other good properties work, and if you take the Cayley numbers and add a new J, you'll get, I think, what's called the Sidonians. Anyway, you can keep getting more and more algebras, and they lose some properties as it goes on, but they're interesting algebras. Yeah.
I'm sorry, I couldn't understand the first thing you said about somebody talked to me. I couldn't understand. I was trying to really listen to you on the slide. You said that a given algebra. You said something about what was new with this slide was that if you take the conjugate and you multiply it, it's not.
The conjugate of the product is the reverse order product of the conjugates.
You said something about that being non-associative or something?
No.
Oh, it is.
That's just if the algebra is non-commutative, then that's the way the conjugates work.
Okay.
But try it out. Take I times j. I times j is k.
Right.
Are you paying attention?
Yeah, I'm writing it down.
I times j is k. The conjugate of k is minus k, right? All right. Now take j bar times I bar. Now j bar is minus j and I bar is minus I, so j bar I bar is the same as ji, and ji is minus k.
Right.
So we just verified that ij bar is j bar I bar.
Okay.
That's all there is to it, really.
Sorry, I got interrupted. I was trying to listen to what you were saying.
Yeah.
Okay.
It's just the way inverses work, but yeah.
It's a very natural way to get into discussion, if you don't mind.
We are discussing.
Okay, good.
Yeah.
And we have time till 1.
Well, how much time do we have? We have about 10 more minutes.
Yeah, sure. Yes, because then we break for lunch anyway. So
Yeah, okay. No, but let's keep going.
Can we
Because I wanted to walk through this history so you could see certain changes
I want you to walk
of point of view, right?
Okay.
So Cayley-Dixon is very interesting and goes up into the present day in the sense that it's not just that you get to the octonians that way, but then you can think about the octonians that way, but also you can go beyond into other algebras by doing it again and again and again. And some people are very interested in that. I never saw anyone really discuss it in detail in a book except Francois Chatelain. But if you were to look on the internet, you would find articles about those extensions. And Francois Chatelain felt that there was a lot of depth, I should say, even though it would be felt. But she feels that there's really a tremendous depth in all those algebras that go on forever coming out of
Francois
it.
Chatelain, I want to look her up.
Francois Chatelain.
How do you spell her last name?
I'll give you the
Oh, okay.
C-H-A-T-E-L-I-N. With a second text on the end.
Now, I thought this was later, but I looked it up last night. I didn't look up when Clifford did his work. But Hermann Grassmann, in 1844, which is around the same time as the Quaternions, he found this amazing generalization of the Quaternions, which is called Grassmann algebra. And Grassmann algebra, and his idea, the reason people don't, it took a long time for people to appreciate Grassmann, partly because of the way he wrote it, and partly because it really involves understanding a little more about vector spaces than anyone had any idea about at the time. But he had a beautiful idea. He said, I want to define a product. I'm trying to create an algebra. And I want it to have the property that when I take two vectors, say in the plane, and I multiply them, then I will get an area for the parallelogram spanned by the vectors. And it should work in n space just as well as in the plane. I want it to work that way. And then what would you need? Well, one thing you need is that the vector wedge is the name of his product. The vector wedged with itself should be 0.
Right.
Because 0 area. And on the other hand, that implies, and then it should have linearity properties, because if you have V and you added W and you look at the area, then you get the sum of the areas. So you get these second two formulas are area sum formulas. And if you multiply by a constant, it should multiply by a constant. So those are very simple properties. But the V wedge V makes everything work in a certain way, because look, if you take the sum of two vectors and wedge them and expand it out according to our rules, you get V wedge V and W wedge W and V wedge W and W wedge V. And the self multiplications vanished, and you got V wedge W is minus W wedge V, so it's non-commutative. So he also comes to non-commutative algebra. And his basis vectors are going to do things that are very similar to the quaternion basis vectors. Ij will be minus ji, but the squares of things will be 0, and it looks like vector cross product there, of course. But it generalizes all of that. And so if you were Grossman and you were writing it down, you might do something like this. You have E1 and E2, and they anti-commute, and they square to 0, and you multiply out, and you see that you get the area, you get the determinant automatically, times E1 times E2. But E1 times E2, what is that? Well, it's just a product. For him, it probably didn't feel bad to have all these multiple products. If he was in 3 space, he would have a lot more products. He would have E1, E2, E1, E3, E2, E3. He would have E1, E2, E3. If he's in 4 space, he's got even more products. So he's getting all these new vectors, which are pointing out in some new spaces. And I think that probably blew people's minds. They didn't quite know how to handle what he was writing. But he was happy with it, and rightly so. And so he invented this algebra, the Grossman algebra, which looks like this. You start with a vector space, and you have a bunch of unit faces, and they all square to 0, and they anti-commute, and then you get areas and volumes and everything working very beautifully geometrically. So out of that desire for geometry, Grossman invents this algebra. And a little later on, people understand that you could have infinitesimals multiplying one another. You could have dx's and dy's in a Grossman form. And they're supposed to be infinitesimal areas, and that will all work.
You get differential manifolds or something.
Right. And the same argument could have been made about differentials. If dx squared is 0, then dx plus dy squared will be 0, and so dx dy should be minus dy dx. The same argument as before. And you can do calculus with square 0 infinitesimals. Nilpotent, I should say, right? But let's move on to Clifford. Because what Clifford does, and I'm not sure the date, is he says to himself, I'd like to combine the essentials of quaternions and Grossman algebra.
1878.
So that means that I'm going to have anti-commutativity, but I'm going to have, well, one way to do it is to have everybody squares to 1. And if everybody squares to 1, then this is looking a little like the quaternions, never mind these funny minus ones, throw them away, and they anti-commute. And we're going to make this into an associative algebra, and it's going to have a lot of products, like E1, E2 is not resolved into anybody else. It's just where it is. So what happens there is that that you get the same thing as happened with the quaternions. You have elements in your vector space spanned by E1 through En, and the product of 2 of them is equal to the dot product, the scalar dot product, added to the wedge product. You see, it's exactly analogous to the quaternion product. You see how that's working. If I take E1, E2, right, then I'm sorry. If I take E1, E2, then they're perpendicular and I get 0. And I get E1 wedge E2. Right.
Right, yeah.
Now, if I take E1 and I multiply it by E1, then I get the dot product, which is 1, and the wedge product is 0.
Yeah.
Right? So you see, you get this geometric, that's sometimes called geometric algebra. So geometric algebra is sometimes described this way, but it's Clifford algebra. You combine the dot product and the wedge product. And when you have the wedge product, then you get all these extra products, all these different products, bivectors, trivectors, all of that. And that turns out to be tremendously useful for lots of people. For example, the person lying down over there. And many people really like to use geometric algebra to do their physics or to do their mathematics. So there we finally got to Clifford algebra. But now what I wanted to do is talk about how Clifford algebra can arise by a process in recursion, which is another point of view about how it comes about. So in this little historical survey, I'm saying Clifford algebra arises because Clifford wants to combine all the geometric things that have been happening about area and volume and quaternion ideas and so on into one geometric algebra. And he comes to this. But I'm going back to I squared equals minus 1 and thinking of it as related to a recursion t of x equals minus 1 over x. I is the symbolic fixed point, but if you recursed, if you kept applying it to itself, starting at 1, you get an oscillation between 1 and minus 1 and 1 and minus 1. And we can think of two views of the oscillation as being plus 1 to minus 1 and minus 1 to plus 1. And there is this desire on my part, at least, to turn that into the square root of minus 1 somehow. The vibration should be turned into the square root of minus 1. And we've already talked about the bottom part of this slide to some extent, but the idea being that I need some algebraic operation that will turn an AB into a BA, right? And what I'm going to do is I'm going to add an extra element, eta, whose square is 1. And if you put eta on either side of the AB, it will turn into BA. Now just take that for the moment as an algebraic convention, a way of describing how to get from the E to the E bar, all right? And then notice what happens. You can think of it as a time shift. And then notice what happens. What happens is that if you take, actually, the next slide will be better. I'll come back to this slide. If I take E and I multiply it by eta E eta, that's E bar, right, by definition. And E bar is minus E. And E was 1 minus 1. Then E squared is 1. So you get minus 1. So this is just formalizing that fact that if I have the plus minus and I apply eta E eta to it, it turns into the minus plus, and you combine them together and you get minus minus, so you get minus 1, right? But now I have an element in the algebra that instantiates it, and that element makes the Clifford algebra. You see it made a Clifford algebra. E by itself squares to 1. You multiply E by itself coordinate-wise, you get 1, 1. 1. And eta by definition has square 1, and eta E is equal to minus E eta. Eta E eta was minus E. Eta E eta squared is minus E eta. Eta E is minus E eta. So that's a small Clifford algebra. So by extending the vibration by another Clifford algebra element, the square 1, we get a 2-element Clifford algebra that then holds the square root of minus 1 as a time-sensitive vibration. And the Clifford algebra is coming up as a natural algebra in which the square root of -1 is enfolded. And of course, we knew that already as far as Clifford algebra was concerned. If I had said to you, let's just take a Clifford algebra and look at the product of the two generators, eta and e, then their square is -1 by the same reasoning. But here I'm interpreting it temporally. And I think the temporal interpretation is interesting, and you can see how it weaves back and forth through various things. So I wanted to mention that, and we're nearly out of time, so let me just jump across a couple of things, but not completely. If you just take this guy, the simplest Clifford algebra, notice we needed their product, and then we need plus and minus for each one. That's called the split quaternions. And one reason why it's called the split quaternions is because you can turn it into the quaternions by multiplying by one commuting square root of -1, one extra one. You just take it out around like a rabbit out of a hat and put it in and multiply to form IE and I eta and eta E and call those I, J, and K. And now you see I squared is -1 because of the square root of -1. And J squared is -1. And K squared is -1 because eta E squared is -1. Internal to the Clifford algebra. And IJK, when you multiply it out, you get -1. So you have the quaternions. So the quaternions come out of Clifford algebra in that way. That's one way. And another way in which the quaternions come out of Clifford algebra is by taking a Clifford algebra generated by three things, okay? A, B, and C, forming a Clifford algebra, all square root of 1, all anti-commute with one another. And then you form AB and BC and AC. And now look at what happened. If you multiply I times J, the B is squared to 1 and you get AC, so I times J is K. And all the rest works out beautifully, and you get the quaternions. So the quaternions are in there in various ways like that. Now, I want to skip this.
We have an hour over time.
Because we don't have a lot of time. Was there a question?
No, it was
Okay.
Go on it.
I just wanted to tell you about the project that I would have told you about if we'd had another hour, but we don't have to go through it. It's a nice project. The project that I got involved in with myself was Clifford algebras are associative, but there is a technical problem. If I write down the Clifford algebra generated by E1 through En, and I say, okay, these relations, but how do I know it's associative? And I will find myself going through some very interesting foolings around to check that it really is associative, because you have all this anti-commutation going on, and you have to check that it really is associative after all that. Okay? So why not have an inductive method of producing them that always produces a new associative algebra? Why not have something like the Cayley-Dixon formula, but for Clifford algebras? Well, here's one way to do that. I'm going to assume that I have an algebra and it has an involution. All right, that's an order 2 operation, which I'm writing star. And it's like conjugation, but you'll see what it's going to be in a moment. But just assume that you're at an algebra with an involution. And then I'm going to add a new element whose square is 1, just like with Cayley-Dixon. You add a new element whose square is 1. And then we're going to have that eta, like we did before, is going to be the involution applied to A. Okay? And we will then define the involution on the new algebra this way. It's the involution on A and the involution on B with a minus sign there. And then this works. Okay? This will, out of its own workings, produce the next Clifford algebra and the next one and the next one and the next one. And you can start with whatever algebra you like. So you might wonder, and I hope I wrote it on the slide,
Could those be like generators as well?
right. So you see that it follows from my construction that eta itself star is equal to minus eta. And that's what the stars will be if you started with, suppose you started with E1 and E2 and you had that nice little Clifford algebra and you wanted a new one. Then the involution is that each one of those goes to its negative. That's the involution on the original algebra, and then you make the new algebra by this formula, and then you verify. It's something only a mathematician would love, but the idea of doing it is having it is a good idea, because then I can verify that in my new algebra, if I started with something associative, I get something associative. Unlike Cayley-Dixon, which won't necessarily induce associativity. So then I know that if I want to produce the Clifford algebra on E1 through En, I just do this thing n times, starting with nothing, and or do it n minus 1 times, starting with E1, and then I will have it, and it will be associative.
So is the crucial difference between this and the Cayley-Dixon is that you're guaranteed to get associative algebras? And it's the crucial difference that gives you the guarantee of associative algebras, that eta involution?
That's right. That's right. So the new element that you add instantiates the involution.
Right. Okay. So that's because when you get Cayley-Dixon, you're not still getting that you're not getting that instantiation.
All right. You can write this down in parallel with Cayley-Dixon, and you'll see the differences in what I'm doing. But what I'm doing is much less finicky than Cayley-Dixon, right?
Yeah.
Because I'm producing much simpler basic algebra structure. But then it does actually then let you play some interesting games and see, oh, well, what algebra do I get when I start with this and I do that and this and so on, and you can have some fun.
Can I make a suggestion that you continue however long?
I'm sorry.
Anton wants to ask something.
Okay.
But I will continue as long as.
Are we out of time?
If anybody want, we have an hour overview only.
Yeah.
That's all right.
Right.
Yes.
So what should we do? Should we just stop?
That would be great if you want to do that.
Yeah.
But you can continue if you want. But Anton has a question which may be quite. Anton, can you come on with the question, please?
Hello, Lou. Can you hear me?
Yes.
Okay, thank you. Lou, I've got a question for you, or if I have a 6-dimensional space that is or let's start with a 3-dimensional space where each axis is a complex plane, which makes it a 6-dimensional space. Now, working in that space, I can define each coordinate as a complex number. But equally well, I could define each coordinate as a quaternion, because now I can have a coordinate real x plus imaginary x plus imaginary y plus imaginary z. Do you know of any vector algebra that uses this sort of common quaternions to define coordinates or to define the coordinates, the 3 coordinates as quaternions?
What's the question?
I'm looking for a vector algebra that can handle quaternions, where each coordinate is a quaternion in a 6-dimensional space. In other words, x, ix, y, iy, z, iz.
Yeah, I'm still not quite sure what it is you're trying to do. Are you saying that each you're going to have n tuples or triples, and the entries are going to be quaternions?
Well, let's put it this way. If I have let's just make it simple. I have a vector along the x-axis. Now I can work in a 6-dimensional space where that vector on the x-axis is x plus ix. But I could equally well, because I've got the imaginary...
Recording stopped.
I have the imaginary...
just the best way to
X
do
is
this.
IY and IZ.
Yeah, and Tom, I think probably the best way for us to do this is if you were to write this out as a question on a sheet of paper and take a shot of it and send it to me in the email, and I'll write back to you. Because I'm very
Understood.
algebra in my head, and I'm sure we could see our way clear to the question that way.
Fine, thank you.
Yeah, but please write to me. Yeah.
Okay.
Okay.
Right. Thank you. I think discussion can continue in couloirs.
Right.
We have now lunch break and we reconvene, say 5 to 3. Yeah?
Yeah.
We're starting at 5 to 3. Right. To make sure that everybody comes, because we have AGM at 5 to 3 at 3 o'clock. So please, young people, do come for the AGM.
Thank you for listening. I hope you enjoyed this sort of historical thing. What?
AGM 3 o'clock, not 2:30.
You do?
No, it's at 3 o'clock, as it says in the...
Said this to us.
Yeah, we also have a more up-to-date
Sorry. I mean, it's... Nobody sent me a new program, so... I do not know...
This is the latest program.
This presentation.
Yes.
Nobody told me about the stream, okay?
We have.
Yeah, thanks.
Can we get the
I won't be able to be here in yet. You can put it ours.
same the new version of that?
Today, not actually. We're going to talk. Dinner, yeah. Come on, yeah. I know you're still going.
So I'm not responsible for the program.
I thought that this might generate some conversation for us because we're both interested.
Yeah, I know. Email and I thought there was
What about Yeah.
okay, but it's out on there. Yeah, we got talking about that. 3:30 and 4:30.
They're like infinite rotations, infinite numbers.
The algebras are
Right.
there are concrete examples of the algebra to think about.
I don't know who
You
is
think of exponential certain entities, exponential rotation.
We need to switch off the sorry. It's right to say that, but
Yeah, I do. Oh, yeah. Just checking for my precious.
yeah, well done.
2:30 we come back for AGM. Anybody? 2:30.
Consider rotations in free space, right?
Yeah.
Now those are matrices such that
You want to go to Cafe Nero?
transpose.
Yeah, I think so. There's something to eat. That's it.
Reverse.
Well, we got 2.5.
Transpose.
So 1.5 hours. Yeah.
And each other. The point is
We go to Cafe Nero.
that every rotation can be represented as the exponential of another matrix. And that matrix satisfies some condition like scarce symmetry. And those are the Lie algebra. That's the algebra. The matrices is exponentials of rotations of other Lie.
If you can get that big table for us.
You have symmetry.
After you, then I'll remember it.